All right, so in this section, it's a little different when it comes to these type of equations. We're actually not going to be graphing them, and you'll see why in a little bit. It's very difficult to graph polar coordinates. What we're going to be doing is pretty much converting it to its a rectangular form and just leave it like that. And you'll see how it goes on a little bit, so don't stress too much. This is going to be a pretty interesting section. Basically, the reason why we just go over this is you probably won't even see this until the second semester calculus, and even then they go over even more. So it's just a quick rundown of what you eventually see itself. So that's why we're not going to go too seriously when it comes to the actual graphing. Okay, but what I want to do real quickly is how to plot points on the rectangular plane. So I have a little template here for you guys, and this is also in your books as well. And we're just going to do a couple examples how to plot points. So let's suppose we want to plot the point 2 comma pi over 4. Okay, so remember in polar it's r theta, right? So the radius and theta itself, right? The angle. So when it comes to this one, right, we go to pi over 4, which is this whole line here, right? That's the angle goes to, so this is pi over 4. And now you get a radius of 2. So starting from 0, you go 1, 2. So you want to see that's when they cross right there. So the radius goes on the x-axis. Here's 1, 2, 3, 4, -1, -2, and so forth down the line in the opposite direction. So that's how you would do it, right? Plot it. So if you would see like an actual one made up for you, because it's pretty difficult to do on your own, that's how you kind of plot it when it comes to these type of portions. So let's try another one. Let's try 3 comma 2 pi over 3. So same thing, 2 pi over 3 is the angle, so we go to 2 pi over 3, which is here. So it's going to be this line crossing up and down. And then we want to go to radius of 3, so which is radius of 3 is here. If you notice, you just follow a circle until you get to the 2 pi over 3, which is right there. So that's the point 3 comma 2 pi over 3 in polar coordinates. Okay. And you do the same thing if it's negative, right? So you just go in the opposite, so it'll be -1, -2, -3, and just go in the opposite direction. So it'll be down here instead when it comes to it. But that's pretty much how it's going to be. We're not going to go too much in crazy when it comes to these type of functions because it get pretty messy pretty quickly. Okay. So we'll just define a polar equation. So a polar equation is an equation whose variables are polar coordinates. Will make sense, right? And called polar equation. The graph of the polar equation contains all the points that satisfy the polar equation. So like I said, right, the main focus about this time is we're not technically going to be graphing. So even in your homework, when you ask a graph, all you're really doing is pretty much converting this into either a rectangular portions or just straight line itself. And you'll see that in example 2. Okay. So first one, we want to graph the equation r equals 2. Now this is kind of weird when it comes to it because if it's r equals 2, if we go back a section, right? So if I go up here, r equals 2. What this is saying, it's a vertical line going up and down at r equals 2, kind of like the x values, right? So if you go over here, you literally have a line going like that, which is pretty crazy, right? Now, if you want to know how that looks out in the rectangular plane, is we go back a section, right? What if I want to convert this to a rectangular plane? We have to square both sides. So we get r squared is equal to 4. And we know r squared is x squared plus y squared. So essentially we get a circle, which we'll talk about also later on in the course, but this ends up being the equation of a circle with a radius of 2. So everything comes into play is this entire circle ends up mapping to a straight line in the polar coordinates because of r equals 2 itself. You could think of it like x equals 2 when it comes to that kind of stuff. So pretty interesting thing from there. But again, the whole focus is pretty much you're probably just going to give me this and be done with it when it comes to it. So these couple examples I'm showing you is just how that actually look like, but I'm not going to make you actually graph them itself, things like that. Okay. So for instance, let's go to the other one. So graph the equation theta equals negative pi over 4. So like I said, this is also pretty tricky, right? So we can't convert it because there's no r, right? We can't square it. So this, like I said earlier, since x, we kind of relate to r, it's this portion. So therefore, y you can relate to theta. So the y theta is going to go this way. But we want the entire negative pi over 4. Well, negative pi over 4 is down here. It starts here and goes straight across. So literally, that is the equation of theta equaling negative pi over 4. So I'm just going to give you a quick sketch of how it will look like. So here's negative pi over 4, and you literally make a line like that. Okay. So again, right, because it's not completely a, so remember, if you go to the xy plane, we have boxes, right, representing those portions, so dot, dot, dot. Here we have curves, so it's, circles. So this line is rotating all the way around, hence why we have a dashed line like that. Okay. Right. So if we flip the page, we'll do one more example. So graph the equations r equals sine, r sine theta equals 1 and r cosine theta equals negative 2. Now these are actually very tricky because if we convert these, right, going back a section, r sine theta ends up being y and r cosine theta equals x, right? When we go about the conversions, that's in the section 9.1. So essentially what they're saying is this represents y equals 1 and x equals negative 2. Okay, so if we go back to our polar coordinates, these are actually going to be straight lines and vertical lines. So we know this one, right? So x equals negative 2, so x equals negative 2, and it's a straight line going up and down, right, vertically. And then y equaling 1, that means on the y squared equals 1, we go across like this. Okay, so like I said, right, these are pretty weird, and it's kind of hard to get a grasp on, especially if we're not going to see them for a long time, especially in calculus. But it's just, again, it's a brief introduction of what the polar coordinates look like in, graphing wise itself. Okay, and I give you guys this definition here. So the theorem says if we have r cosine theta equals a, and the graph is a vertical line, so it gives you the straightforward, definition here. So if whenever you see something like this, it is automatically a vertical line going up and down from the polar A. And if we have r sine theta a, we automatically have a horizontal line. So those are the only major concepts when it comes to those. So those for sure, like right off the bat, it's going to be vertical, horizontal, if they follow that template there. Okay. Now, for the rest of them, when it comes to, so example 4, example 5 down here, again, we're not going to be completely graphing them. All I really want you to do is basically convert this to its rectangular plane and be done with it. That's it. So from there we can actually graph them. And some of these we don't know how to graph yet because like I said earlier, we haven't talked about circles too much yet, but just repetitive. So let me show you. So for example 1, it says r squared equals negative 4 sine theta, right? Now I said earlier, right, r squared is x squared plus y squared, just going back a section, right? So this is equal to, and we know this whole thing is y. This is negative 4y. That's it. So this is what I mean by be done. So we're not completely graphing it. You can leave it just like that, and we'll be done for it when it comes to it. Okay, and we can keep going. So if we go over here, so r squared is x squared plus y squared, and now this one is going to be 2x, right? Because that represents x itself, and that's it. Okay, so this stuff we can actually graph, our own, but for this section we're just going to go by that kind of stuff. Okay, right? So let's try the next ones. So given the graph r equals 7, same exact concept like I did above in the last example, right? So it's identically like the one here. Just convert it and be done with it, right? So for here, how do we convert it? We have to square both sides. We have r squared is equal to 49, right? And then we have x squared plus y squared is equal to 49, so we have a circle as well. Okay. All right, so why don't you guys try the rest? I'll give you a quick pause, so 3, 2, 1, pause. Try them. Okay, so let's do the rest of them. So again, right, this is x, so this is be 4 equals x. That's a vertical line, right? According to our definition, right? It's exactly what our vertical line represents here, right? Down here, we have x squared plus y squared is equal to, we don't have an r. Well, that's interesting. So we can't actually do that. So remember, when it comes to conversions, we have to multiply by r. So we have r squared times r is equal to 2r cosine theta, and you'll see why I do that right now. This is a trick question. So now we know r squared is x squared plus y squared, and we know r is radical x squared plus y squared, and now this is equal to 2x. So it may look funky, but we can technically graph that as well. Okay, but that's it. That's all we're doing when it comes to that. Okay. All right. And last one, theta is equal to 3 pi over 4. So same as concept as the last one, right? You know, you could just quickly do this one. This is 3 pi over 4 right here. Oh, 3 pi over 4. Down here. It is like that.